Hello and welcome to Lecture 16. In this lecture, we're going to continue our discussion of binary relations. So to start with, we're going to define a new type of binary relation, namely a transitive relation. A relation R on a set X is transitive if, for all x, y, and z in X, whenever x and y are in R, and whenever y, z is in R, then this implies that x, z is also an element of R. So let's go through some examples. The relation equals on R is going to be transitive. So explicitly, whenever A is equal to B and B is equal to C, we know that that implies that A is equal to C. So now let's look at another operator. The equals relation for sets. Do we think this is going to be transitive or not? Well, it is going to be transitive, since if A is equal to B and B is equal to C as sets, then this implies that A is equal to C also as sets. Next, what about the relations equiv applied to the set of all propositions? Is this going to be transitive? Well, again, yes. If P is equivalent to Q and Q is equivalent to R, then P and R have the same truth values, therefore P is equivalent to R. One more. What about the greater than relation on R? Is this going to be transitive? Well, yeah, since if I have A is greater than B and B is greater than C, then this implies that A is greater than C. This begs the question, are there non-transitive relations? Well, the answer is yes. One example is the not equals to relation. So the not equals to relation on R is going to be not transitive, since 1 is not equal to 2 and 2 is not equal to 1, but 1 is equal to 1. Okay, so it turns out that a lot of the nice relations that you're used to working with are in fact transitive. Now that we have a new type of relation, we can combine this with the previous relations that we talked about in the last lecture, namely symmetric, asymmetric, antisymmetric, reflexive, and irreflexive, to talk about new types of relations. So for the first type of relation, a relation R that is reflexive, antisymmetric, and transitive is going to be called a partial order. So a set S along with a partial order, say P, is called a partially ordered set, or poset for short. So we can use this notation S, P, or this R sub S, P to denote a poset. So explicitly here, a poset is not just the set and not just the relation, but it's the set along with the relation. So let's look at an example of a poset. R sub z, greater than or equal to is a poset. Why would this be true? Well, let's just go through and show that this is a poset. Well, the first thing we need to show is that this is reflexive. Well, pretty trivially, if I consider any arbitrary integer, that integer is equal to itself, therefore it's greater than or equal to itself. Thus, this is a reflexive operator on this set. Next, is this antisymmetric? Well, how do I show that something's antisymmetric? Well, I need to show that for all x and y and z, if x is greater than or equal to y, and y is greater than or equal to x, then x is equal to y. Would this be true? Well, yeah, it is true for this case. Therefore, this is antisymmetric. Next, we need to show it's transitive. So how do I show transitive? Well, I need to show for all x, y, and z in z, if x is greater than or equal to y and y is greater than or equal to z, I need to conclude now that x is greater than or equal to z. Can I do this? Well, yeah, that's true for integers. So thus, since r sub z greater than or equal to satisfies all of these properties for all of the elements in z and for this relation greater than or equal to, this is a poset. So one thing to note, posets allow me to build chains of elements. So here the chain's kind of trivial. For any given integer here, if I draw my integer line as positive integers go this way, and negative integers go this way, for any given element, this will be related to all elements that are less than it. So I kind of have this little chain that builds up where I have all of these integers down here. And then if I increment by 1 and consider the next integer here, I then have the collection of all the integers less than that. So from here, I can kind of build a nested set. So to be explicit, I have that the collection of all the things that are related to -1 will be a subset of the collection of all the things related to 0, which is a subset of this collected to 1, the collection that's related to 2, etc. So for this example, the chain that I'm talking about building up is kind of trivial, but let's elaborate on this a little bit more by looking at another example. If I am given a set A, then this collection of the power set of A with the operator subset of is a poset. Why would this be true? Well, for all x in the power set of A, trivially, S is a subset of S, therefore this is going to be reflexive. Further, for all x and y that are elements of the power set of A, if x is a subset of y and y is a subset of x, this implies that x and y are equal to each other. Thus, this will be anti-symmetric. And finally, for all x, y, and z in the power set, if x is a subset of y and y is a subset of z, we know that x would be a subset of z. Thus, this will also be transitive. So let's look at all of the subsets of this set A for A is equal to 1, 2, 3, just for a concrete example. So we know there's 2 to the third or 8 subsets of these, namely the set that contains nothing, 0, the sets that contain 1 element, the sets that contain 2 elements, and finally the set A itself. So we can draw these in a handy-dandy little diagram to show these chains that I was talking about. So explicitly, here these little lines denote subset of, and I read this diagram from the bottom going to the top. Formally, I could put little arrows here, but I didn't do it in the original picture just because it's kind of a pain to do that in Tix. So here, what is this really saying? Well, this null set is, say, a subset of 3, which is a subset of this set, which is a subset of that set. So I kind of have this nested chain going this way. I have another chain going, say, this way over here, or another chain going that way, or just for completion, one chain going here, and then 2 chains going this way. So it gets kind of messy when you draw all the little chains in, but this is what a poset really does. It lets me relate various elements with other elements in a way where I can build up these little chains of inclusion. Okay, so now that we've talked about posets, let's change topic a little bit and talk about strict partial orders. A relation R that is irreflexive, antisymmetric, and transitive is called a strict partial order. So notice here that the difference between a poset and a strict partial order is that instead of being reflexive, we're now irreflexive. So let's give a few examples of strict partial orders. Our z greater than is a strict partial order, and for any set A, the power set of A along with the subset operator here, where I'm only taking proper subsets, is a strict partial order. So for a theorem, the only relation that is both a strict partial order and a partial order is the null relation. So this theorem is not very hard to prove, so I'm just going to leave that as an exercise. And again, I'll probably put that as your extra practice problems. So finally, like with posets, strict partial orders also defines those chains that I was referring to earlier. And in fact, I'd actually have the same diagram here, with the only difference being in this diagram as a poset, I'm allowing this set to be a subset of itself. But if I was using the proper subset operator instead of the subset operator, I wouldn't allow this set to be a set of itself within my diagram. And here's a meme about a common misconception. So now let's change topic again. Equivalence relation. A relation that is reflexive, symmetric, and transitive is called an equivalence relation. So you're actually familiar with equivalence relations. You've used them in the past, and I've introduced some of them during this course. So let's give a few examples. The relation equals on R is an equivalence relation. Why? Well, just for all x and R, x is equal to x, therefore this is reflexive. Further, for all x and y in R, if x is equal to y, then y is equal to x, therefore it's symmetric. And finally, for all x, y, and z, if x is equal to y and y is equal to z, x is equal to z, therefore this is transitive. Thus, equals is an equivalence relation. That's kind of where we get the name from. Further, logical equivalence to on logical propositions is an equivalence relation. Literally just go through the same argument here, but replace R with the set of all logical propositions. Next, equals on sets is also an equivalence relation. Again, replace R with a set of sets and you're done. Next, the relation greater than on Z. Well, do we think this is an equivalence relation? Well, no, this is not going to be an equivalence relation. Well, for one, X is not greater than X for any fixed value of X. Next, the subset relation is, again, not an equivalence relation. Every set is a subset of each other, so it would be reflexive. And if A is a subset of B and B is a subset of C, then A is a subset of C. So it is transitive, but it is not symmetric, since there are sets that are subsets of other sets that aren't subsets when you swap it. So for example, the set 1, this is going to be a subset of the set 1, 2, but I can't go the other way here, right? This 1, 2 is not a subset of 1, therefore it's not symmetric. Okay, so let's look at another kind of more complex example. So the relation R on Q defined by this P1 divided by Q1, P2 divided by Q2 is an R whenever P1 Q2 is equal to P2 Q1, where the equals here is taken as the standard equivalence relation on Z. So what I mean by two integers being equal. Prove that this is an equivalence relation on Q. So previously, when comparing Q to Z cross Z plus, I had mentioned that in Q, I can have two fractions that are equal to each other, even though they don't have the same numerator and denominator. And thus, I needed to do something a little bit fancy when talking about elements in Z cross Z plus being equal. If I truly wanted to define Q as Z cross Z plus, well, this is explicitly what I need to do. So this expression here might look kind of weird, but let's just kind of see where it came from before I actually prove this. So if I have two fractions, P1 over P2, or P1 over Q1, and P2 over Q2, these two things will be equal if and only if I say multiply this side by Q1, well, multiply both sides by Q1 and both sides by Q2, which would give me P1 times Q2 is equal to P2 times Q1. So this expression here is exactly what I'm requiring this relation R to do on Q. So that's where this comes from, and this is the way that you formally define the rational numbers, is two rational numbers are equal if and only if this statement here holds. So in order to be able to define the rational numbers that way, we need to show that this is an equivalence relation. If it's not an equivalence relation, then it doesn't do what we want it to do on Q. So let's do that. So to prove that this is an equivalence relation, we need to show that it's reflexive, symmetric, and transitive. So let's do each one of these one at a time. So for all P and Q in Q, we need to show that PQ is related to PQ. So explicitly, we need to show that P times Q is equal to P times Q. Well, that's trivial because P times Q is equal to P times Q in Z. Thus, PQ is related to PQ, and therefore, this is a reflexive relation. Next, we need to show that it's symmetric. So how do we show that something's symmetric? Well, we consider two elements of the set, and I assume that they're related to each other. Well, if this is the case, then I know since these two things are related, that this expression here holds. So explicitly, I know that P1 times Q2 is equal to P2 times Q1, like so. And from here, I now need to somehow conclude that the relation holds the other way. So how can I do that? Well, these things are integers. So I can simply note that since equals is symmetric in Z, I can swap this order. So P2 Q1 will be equal to P1 Q2. Thus, from here, I get that P2 Q2 and P1 Q1 are related. Okay, so from here we have that this is symmetric. So now we need to show transitivity. So to show transitivity, I need to show for these three pairs, if is related to the second pair and the second pair is related to the third pair, then the first pair is related to the third pair. So here I have a bit of non-trivial, in some sense, algebra to do. Well, by definition, if these two are related and these two are related, that gives me these two equations here. So I now want to ultimately conclude that P1Q3 is equal to P3Q1. So to show this, I have to use these two facts somehow. So the trick for this one is I multiply this equation here, the left-hand side by this expression and the right-hand side by this expression. I can do that because these two things are equal, and I know I can do that in Z. So from here, multiplying that through, I get this expression here. So again, I multiplied this side by this P2Q3 and this side by this P3Q2. So now that I have this expression, I somehow need to conclude that this thing here is true. Well, if I look at what the difference on the left-hand side is, here I have a Q2 when I don't want a Q2, and here I have a P2 when I don't want a P2. Similarly, over here, I have a P2 that I don't want and a Q2 that I don't want. So in order to cancel this out, I have to consider two cases. One, if P2 is not equal to 0, I know automatically that Q2 is not 0 because it's a rational number. Then I can divide by this thing because it's non-zero. It cancels out these two terms here and these two terms here and gives me exactly what I want. On the other side, if P2 is equal to 0, then since these two things are related and these two things here are related, that implies that P1 has to be 0 from this relation and P3 has to be 0 from this relation. Thus, from here, we trivially have that this holds because 0 equals 0. This implies that this is related to this expression here, which is exactly what I wanted for transitivity. So if I was writing a formal proof here, I might put an extra line kind of off the bottom side of the screen saying, thus R is reflexive symmetric transitive and therefore an equivalence relation on Q. But here I just don't have enough space for that, and yeah, I decided to go with this so that you could see the theorem and the proof at the same slide, but it's kind of unfortunate that I don't have enough room. Okay, so this equivalence relation that I've just defined on Q is what it means for two fractions to be equivalent to each other or to be equal. Okay, now let's look at another slightly more exotic example that you may have seen before. Let x be in Z, let y be in Z plus, and let y be an element of the set from 0 to y minus 1. So from here, for any given value of x, or for any given value of y, I'm defining this set that R is in. We say that x mod y is equivalent to R, or equal to R, or congruent to R. Those are all terminologies I can use here. If there exists a q in Z such that x is equal to qy plus R. So from here, this R is the remainder when I take x and divide it by y. So for any n and n, RZ mod n, which will be equal to this relation here. So explicitly, the pairs of integers x, y, such that x mod n is equal to y mod n. So here, x mod n is going to be some number between 0 and y minus 1. So by this equals, I'm using the equals in Z, and not the equals here. This relation is an equivalence relation. So let's prove this real quick. So we want to show that for any n and n, mod n is reflexive, symmetric, and transitive. So to show that it's reflexive, I take some x and z, and I simply note that if I take x and divide it by n, that will give me an integer r, and if I do the same thing over here, that will give me this remainder r when I compute this mod, and r is equal to r from the equals in z, therefore this is true. Secondly, for all x and y and z, if x mod n is equal to y mod n, then I need to conclude that y mod n is equal to x mod n. Well, this is trivial because x mod n is just going to be some integer, y mod n is going to be some integer, and if these two things are equal, it's going to be the same integer. So by the symmetry of equals in z, I simply get that this is equal to that, therefore this operator here is symmetric. Next, I need to show transitivity. So to show transitivity, let x, y, z be in z, and I want to assume that x mod n is equal to y mod n, and y mod n is equal to z mod n. Well, again, I use the exact same argument that I made earlier. These things are just going to be integers, and equals in the integers is transitive, therefore this will be transitive. So here you can say that this mod n relation is endowed with this reflective, symmetric, and transitive properties. from the same properties for the equals relation in Z. Okay, so that's what equivalence relations are. It's basically a formal way of saying things are equal to each other. We now have one last thing I want to introduce, and this is the idea of equivalence classes. Equivalence relations induce collections of elements of a set that are equal called equivalence classes. So here, this really isn't a definition of equivalence classes because all I've really told you is that equivalence relations induce equivalence classes. So let's give a definition via example. So consider the relation mod 3 on Z. So explicitly, this is saying given any number in Z, divide it by 3, find out what its remainder is. That's what I'm going to set the number equal to. So we can notice that the elements of each of the following classes that I'm going to write here are related to each other under the mod 3 relation. So explicitly, 0 has the same remainder when I divide it by 3 as 3 and negative 3, as 6 and negative 6, and I can keep going on each side forever. Similarly, 1 has the same remainder when I divide by 3 as 4 does when I divide it by 3, as 7, negative 2, 5, etc. And finally, 2, when I divide it by 3, has a remainder of 2, so does 5, 8, negative 1, negative 4, etc. So kind of one little caveat to notice here, this minus 1 has the same remainder when I divide by 3 because I require that remainder mod 3 to be equal to 0, 1, or 2. So there's a couple things you can notice here. One, these sets have nothing in common, right? 0 is in here, but it's not in these sets. 3 is in here, but it's not in these sets, etc. This is generally true for equivalence relations, and a good exercise would be to prove that. I mean, it's pretty trivial. If these things have something in common, then everything else that's in this set also has to be in this set. So you end up with the two sets being exactly identical. And if they don't have anything in common, their intersection will be the null set. Further, I can note that every integer appears in at least one of these. Well, at most as well. So Z is the union of these three sets, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and I can count negative that way. These three sets, when I union them, contain all of the elements in Z. So we have a name for this. A partition of a set S is a collection of disjoint sets S sub I, such that the union of S sub I for all of the i's that I need to union over is equal to S. For instance, in this case, this partitions Z into 3 sets. So now we could ask, is this a fluke? Is this only something that's true for this operation? Well, let's look at another example. The relation equals on Q induces infinitely many equivalence classes. So explicitly, I have the class of 1, which is equal to 2 over 2, 3 over 3, etc. I have the class of, say, negative 1 that's equal to negative 2 over 2, negative 3 over 3. Here, the negative is in the top, not the bottom, because in Q, I'm restricting myself so that the denominator is always positive. Further, I have, say, like the class of 1/2, which contains elements like 2/4, 4/8, etc. So this process goes on forever. I have infinitely many distinct fractions. Therefore, there are going to be infinitely many of these equivalence classes. It's pretty easy to see. For instance, just consider fractions of the form 1 over n. And then notice that these sets have no common elements. Again, they can't, because if they had a common element, then they have to be the same set. And Q is going to be the countable union of these sets. So why do I need countable union? Well, this is going to be countably infinite. Okay, so now let's give you a theorem. An equivalence relation R on a set S induces equivalence classes that partition S. So here I may or may not have a finite number of equivalence classes. It's generally more useful of a property when I have finitely many equivalence classes. And these equivalence classes could only contain one element. For instance, the equals operation on Z, each class would only contain a single integer. So that is it for equivalence classes. If you have any questions on these, ask during office hours on Piazza. So we have some assigned reading. Read pages 56 through 60. So here in the text, they go through the example for showing that mod 4 is an equivalence relation, so it might be useful for you to look at that. And it goes through a few other posets that might be interesting to look at. So from here, we have our meme. When you have an equivalence relation, partition the set into equivalence classes. You can always do this. It may or may not be useful to simplify the algebra of the system, but this is what an equivalence relation will always do. Okay, so I will talk to you guys in the next lecture and see you then.